Connaissance.
Recherche.
Sciences.
Des mathématiques.
Théorie.
Physique.
Philosophie.
Conférence.
Archéologie.
Environnement.
Nature.
Okay. Martin actually gave the introduction to ontogenetic stages in sauropods, and we wanted to, as we're interested in gigantism and in body size increase, we're also interested in size decrease and in body size evolution in the other spectrum. So we have now two known dwarf sauropods. The first one that I'll be talking about is Magyarsaurus dacus from the late Cretaceous of Romania, which has already been described by Nopcsa in 1915 as a dwarf sauropod. And the second dwarf sauropod I'll be talking about was discovered more recently, and it's from the late Jurassic of Germany. So without further ado, this is just a phylogenetic framework. So Europasaurus is a very basal, like macronarian, and Magyarsaurus, although it needs some redescription, is now plotted as a derived titanosaurian. So the main question that we're interested in these dwarf sauropods is how did they adapt to their ecosystem? Independent of what causes them to reduce their size. We've heard a very nice talk about this by Mike Köhler this morning. And there's several possibilities to do that. Either you reduce the adult size and retain the ancestral growth rate, or you do reduce the metabolic rate or reduce the growth rate. But these probably are correlated with each other, as we've seen earlier today. So we want to quantify the growth rate in these dwarf sauropods. I won't have to explain all this. That's very good. We can skip that. Okay, that's not good. All right. So Magyarsaurus is known from a large number of isolated postcrania. And as I said, Nopcsa had already thought it was a dwarf sauropod, as he compared those with the large sauropods from the Morrison Formation that had been coming out. And by the way, these data have been published recently in PNAS. And just to give you again the phylogenetic framework, this is Europasaurus and this is Magyarsaurus. This is a character optimization of body mass, of femoral length, and you see that these two immediately jump out. So this is the largest known element of Magyarsaurus dacus, and this is the smallest known element. And in 2005, Jean Leleuf published a paper where he described this very large humerus that came from the same localities as Magyarsaurus dacus. And he mentioned, well, this is just a continuous ontogeny. These are the adults. Those are all juveniles. I have to mention before, this is a estimated 90 centimeter humerus. This one is estimated to be about 50 centimeters. And that would mean a size increase between the largest Magyarsaurus dacus and this one particular humerus of 5 to 6-fold. So that already raises a few questions. And so we went on to sample the fossil material, the collections. So we got, this is a peculiar, I have a funny anecdote about this, but we were denied access to the British Museum, so we were very happy to get access to all these collections. And we used the core drilling method that Martin just described in the last talk. And going on to the histology, this is a humerus of Magyarsaurus in normal polarized light, and if we cross polars, immediately see full of secondary osteons with maybe some remnant primary bone left here and there. Going on to another section, tibia, 30 centimeters long, and again, completely remodeled. And if we zoom in on the primary matrix that is left in some of these specimens, we see a large portion of lamellar bone and parallel fibered bone, indicating slow growth. And furthermore, if we look at some larger specimens, we see cross-cutting relationships of secondary osteons, indicating that there were several generations of remodeling going on in these specimens. Here again, cross-cutting relationships right here and right here. Also, I have to indicate that we were not able to find an external fundamental system that would indicate stop of growth, but that's because you can see here that the outer surface is truncated due to either taphonomy or maybe even preparation, the rough mechanical preparation. And some specimens preserve a little bit more primary bone, as in this one. This is the very smallest humerus that we found, in the collections, that is. And as you see, it retains, although it's badly preserved, it retains the laminar organization that is typical for sauropods, so well vascularized. And if we then look at the very large humerus that was supposed to be the adult of these, it actually shows the same ontogenetic stage as this very small humerus. So this indicates, if we put these on a Haas diagram, that the large humerus is actually not on the same growth trajectory as these small Megarosaurs. So therefore, we were able to distinguish that they're actually two different taxa. So as Jack Horner presented in his talk, we're not able to just put different taxa on one ontogenetic trajectory. We're also able to actually, presumably, one taxon to actually pull them apart and name different, well, not naming them, but actually indicate that they are different taxa. But the secondary modeling actually limited us from quantifying the growth rate in these animals. But as you see here, Europasaurus doesn't have the extreme remodeling. So moving on to Europasaurus, we also have an ontogenetic series of long bones, and we do preserve the primary growth record that does show growth marks. So we were able to construct a growth curve. This is some of the material that we sampled. So this is a femur, I think, the largest one, and this is the smallest one, also a femur. It was a tibia. But anyway, the smallest tibia shows reticular fibrolamellar bone, but no growth marks. The second one shows, these show up better under microscope, but still active growth, new vascular canals becoming incorporated into the bone matrix. Already, no, this is actually diagenesis. This is not secondary osteons. But there are growth marks in there. The next specimen also preserves these growth marks, still active growth, becoming more laminar, as we also see in other sauropods. And then another large specimen, more growth marks. And then this is the very large specimen, but it was drilled very distally, so we cannot use it in a growth curve because it's not drilled in a standardized location. And then using, this is a very famous figure, using methods from the literature, we're able to estimate the ages of the animals, and we were also able to estimate the masses using typical Anderson et al. Formula, and we get a maximum weight for the largest Europasaurus individual of 690 kilograms. Of course, I don't have to illustrate that there are a lot of problems with these methods because we're assuming that the growth marks are annual, and these are indeed minimum age estimates because there is an associated tibia and femur that show a different number in growth marks. The mass, the bones are largely incomplete, and of course, I had to estimate because these are incomplete based on humerus and femur lengths to extrapolate the circumferences. Anyway, if we then put these animals as individuals on the growth curve with the estimated ages and weights, we get a maximum average mass increase of 74 kilograms per year. Now, Martin illustrated that there are models we could use, and with the same evolutionary ecologist, we were able to construct this von Bertalanffy model, and if we put that on the growth curve, we see an inflection point around 11 years. The maximum yearly mass increase is a bit lower than the other method, but at least we can make an average. Plotting these on the case curves, we see that Europasaurus indeed reduced its growth rate and moved away more towards the prosauropod condition, as this is massospondylus. Indicating that there indeed was a heterochronic reduction in growth rate. Now I want to move on to a subject that Tim Bromwich touched upon, and that I became very interested by. And that's this correlation between body mass and lacunar density. And in fact, he found like a scaling, an allometric relationship between these, suggesting that there is that these osteocyte lacunities in fact represent osteoblast proliferation rates, hence local apposition rates. So I did this on several sauropodomorph taxa doing a Z-stack analysis, and if we run through, this is a PDF, so no cool animations, but anyway, so I found the same correlation parallel to the mammals, but higher osteocyte densities as compared to mammals of the same weight. By the way, I got the mass estimates were taken from the literature. This is a frog, just as an outlier, and I also plotted 2 extra mammals, an elephant on this range and the typical guinea pig on the other range, and indicating, of course, that this relation is valid. But why do these sauropodomorphs show so much higher osteocyte lacuna densities? Would this indicate that indeed they have higher growth rates than these mammals? So maybe we can take this even further by actually getting the basal metabolic rates from the lacuna densities, as we know that there is an allometric scaling from the physiological literature with basal metabolic rates. So maybe we could just plot in osteocyte lacuna densities, but probably there is more to this, as this is a bit of work that I did with Chris Organ and Steve Poussati, and we measured osteocyte lacuna densities, and we found that, in fact, osteocyte lacuna densities are very low compared to mammals, and again, in physiological literature, we find that there is a relevance of cell sizes for metabolic rate. This is based on erythrocytes, red blood cells, but Chris, in his 2007 paper, found the correlation between osteocyte lacuna size and genome size. So we definitely need more data on these cell sizes, but they may play an important role in these osteocyte lacuna densities, as there is this huge jump in mammals and other dinosaurs. So if we can extend this database, maybe we can say something more about these metabolic rates in sauropods. So just to conclude, that was very quick. Magyarsaurus stachys was a dwarf, and from Europasaurus we were able to find this heterochronic reduction in growth rate. But the remodeling and high vascularization, of course, indicate that they retained their high metabolic rate and didn't do something similar like Myotragus that we saw this morning. And I also wanted to address the potential of lacuna density in these studies. Now, I just want to thank these people and the DFG for funding, and of course, Michel Laurent and Georges Cubot for inviting me, and you for your attention.